Hello, today we'll be reviewing a first order RC circuit demo. Our circuit is shown in the top left of the screen, and we have a voltage source, a resistor, and a capacitor in series, and we'll be measuring the voltage drop across the capacitor and calling that VO. This is a one-DOF first order system. Using Ohm's law, we know that the voltage across the capacitor is equal to 1 over C times the integral of I. And solving for I, we get I equals C times VO dot. Using KVL, we know that VR plus VO equals VS. And substituting in V equals IR, we get IR plus VO equals VS. And substituting in the current that we found previously, we get our EOM RC VO dot plus VO equals VS. There's two ways to go about solving for the characteristic equation. You can guess and check AE to the ST and take a derivative of that. So VO dot equals AS E to the ST. Substitute both of those back into your EOM and factor out AE to the ST, and dividing through by that gives you the characteristic equation RCS plus 1 equals 0. Solving for our eigenvalue S, we get -1 over RC. And so we know our eigenvalue is inversely proportional to resistance. For first order systems, the eigenvalue is also the bandwidth of the system, and that is the band of frequencies that can be accurately tracked by the system. And so that decreases with an increase in resistance. We can also solve for our time constant tau, which is equal to the absolute value of 1 over S. And so that gives us tau equals RC. For a step response, that means that as we increase resistance, it takes longer for our system to reach our desired magnitude. We can also do the Laplace transform, and that gives us the transfer function 1 over RCS plus 1. And our characteristic equation is the denominator of our transfer function. We can set S equal to J omega to get that in frequency form. And we can plot that on the real imaginary plane, where J is the unit vector for the imaginary direction. Taking the magnitude of that gives us our gain, which is equal to 1 over the square root of 1 plus omega RC squared. So we see that for a frequency response, our gain decreases as R increases. And we can also solve for our phase shift by taking the angle from the numerator and subtracting the angle from the denominator. So we see our phase shift is equal to negative arctangent of omega RC. And so we see that our phase shift increases with an increase in resistance. So let's look at the demo. We're using the Espotec Labrador as our signal generator and oscilloscope. That signal runs through our potentiometer here, and the switch allows us to switch between RC and RLC. So for RC, that signal goes across our capacitor here, and it's measured back by our Labrador, and we see the response. So on the screen, you'll see that the bottom is our input, and the top square wave is our output across our circuit. So as we increase the resistance, you'll see that it takes longer and longer for our system to reach our desired magnitude. And if we keep increasing it, you'll see that it actually doesn't make it, and we get this cutoff here. And so this is simulating a step response or a transient response. And we can also look at the frequency response by running a sinusoidal wave. All right. So as we increase our resistance, we'll see that our amplitude decreases. And we can also see our waveform shifting, and that goes back to the gain and phase we found earlier. All right, well that's it for the RC demo. Let's look at the RLC circuit. For the RLC circuit, you'll see that we've added an inductor in series with the resistor and capacitor. It's still a 1 DOF system, but now it's second order. Using Ohm's law, we know that I equals C times VO dot. We can also solve for VL equals LI dot equals LC VO double dot. So using KVL, we know that the voltage drop across the resistor, inductor, and capacitor is equal to our source voltage. And substituting in what we saw for previously, we can find our EOM, which is equal to LC VO double dot plus RC VO dot plus VO equals VS. Taking the Laplace transform gives us our transfer function 1 over LC S squared plus RCS plus 1. And substituting in S equals J omega, we get that in our frequency form. And taking the magnitude of that gives us our gain. 1 over the square root of 1 minus LC omega squared plus RC omega squared. So we see that once again our gain decreases as we increase the resistance. And we can solve for phase as well. That is negative arctangent of RC omega over 1 minus LC omega squared. And once again we see that our phase increases as we increase the resistance. And so for second order systems, we know that standard form is S squared plus 2 zeta omega n S plus omega n squared equals 0. By normalizing our characteristic equation, we get it in the form of S squared plus R over LS plus 1 over LC equals 0. Using that, we can solve for zeta and omega n. Omega n is equal to 1 over the square root of LC, and so it is not dependent on the resistance of the system. Solving for zeta, we get zeta equals R times the square root of C over 2 times the square root of L. And so we see that our zeta is proportional to our resistance. So we can see how that looks with our waveforms. And we'll just swap over to our RLC circuit and go back to our square wave. All right, so this is the RLC. So you see we get a lot of oscillation there. This is with the potentiometer turned down to almost 0. And as we increase resistance, goes away pretty fast there, but you can see that we get a lot more damping, the oscillations start to die out, and then we end up getting what you would think of as a first order response once the second order transients has died out. Okay, and we can look at how that looks with the sine wave as well. Very similar. We see the amplitude decrease and our phase shift. All right. Well, I think that's all for the RC RLC demo. Hope you've enjoyed watching.